Assalamu alaikum everyone. So this is the 17th lecture of the course Wireless Networks, and the name of today's topic is Wastage Aware Routing. Okay, so what is Wastage Aware Routing? We're going to see a little later on, and you'll see that it's mostly or sometimes it's referred to as WAR or WAR. Okay, so WAR also means Wastage Aware Routing. So let's start. Today what we're going to do is we're going to learn about wastage aware routing from a specific reference research paper. The title of the research paper is Wastage Aware Routing in Energy Harvesting Wireless Sensor Networks. Okay, so you already know what wireless sensor networks is, or what WSN are, but you also need to know what energy harvesting wireless sensor networks are. Okay, so we're going to see that in the next few slides. So the authors of this paper are Martinez, Lee, and Zhao, and the journal where it was published is IEEE Sensors Journal, which is also a very good journal, and the publication was available online, or I think it was published on September 2014. So it was about 6 years ago. So what is wireless sensor network? It's actually a network which has many challenges and which has very limited resources, and we've already learned a lot about wireless sensor networks and some of the MAC protocols of wireless sensor networks in a previous slide, right? And if you remember, then one of the most challenging issues of wireless sensor networks was its limited battery life, or its limited lifetime. Okay, so later on, after wireless sensor networks were invented or made, a specific type of wireless sensor network arose, which was energy harvesting wireless sensor network, or EH-WSN. So the specialty or characteristics of this specific network was that the nodes of this network could harvest or collect energy from the environment. So if they were managed properly, then it could potentially give us a network with infinite lifetime, okay, compared to how the nodes could easily die in wireless sensor networks. Now, as harvesting energy is possible, the network can actually exist for an infinite amount of time. So if you remember, there were four basic or necessary let's say parts of sensor node, and there were a few optional parts as well, right? So there was an optional part which could collect power from the environment. Okay, so that was the energy harvesting unit. So the aim in building energy harvesting wireless sensor networks is that it can assure a long time or a long period of network operation. It can even be infinite. Okay, so there are various route selection strategies, and as we have more options in energy harvesting wireless sensor networks, so we also have to make protocols which consider both energy and distance. Okay, so the routing strategies significantly influence two things. One is the minimizing the energy consumption of the nodes, which is just the normal consumption of the battery life, and also it has to balance the energy depletion. So that means whenever a node forwards a packet, it uses some part of its battery life. So we also have to balance energy depletion and energy consumption. Okay, so this means that if a battery or if a node has very less battery life, then we might have to send a packet to another path which has which might have a longer delay time, but the nodes in that path have a larger amount of battery life left. Okay, so this specific paper is actually a thesis work which focuses on designing an energy adaptive routing metric to meet the energy harvesting wireless sensor network requirements. Okay, so the things that we see here, minimizing energy consumption and balancing energy depletion, so these things are already considered in many other papers, but this paper is special because it considers something else, which is energy wastage. Okay, so this is just an introduction of wireless sensor networks. We already know it, right? A wireless sensor network is spatially distributed autonomous devices using sensors to monitor physical or environmental conditions. We already know it, and there are many constraints, and limited lifetime is one of them. So the recent advance in energy harvesting technology gives promising solution for long lifetime. Okay, that means that if the energy harvesting technology is used properly, the network lifetime can increase by many folds. So the energy harvesting can take many forms. For example, it can derive energy from external sources like solar energy or thermal energy, wind or kinetic energy, or it can also use captured and stored energy in wireless sensor devices. Okay, so usually the solar is the most easy one, I guess, and you might have already seen a lot of solar powered batteries in your environment as well. So energy harvesting sensor networks potentially maintain an infinite lifetime of battery. We have already said that. And solar power WSNs collect power every day if there is sunlight. So this can be used very easily, but the thing is at night time there is no sunlight, right? So yeah, you have to consider this factor, and you have to collect as much energy as possible. So even though it might seem like the energy is unlimited because the sun is always there, for a short time or for a short term period, the energy is actually not infinite, because when there is no more sun, that means maybe at night it can only perform a specific amount or limited amount of transmissions. After that the energy will be depleted. Similarly, even during daytime, if the amount of transmissions done by a node exceeds the amount of energy it can harvest at a time, then also the node may die out. Okay, so in long term the energy may be unlimited, but in short term the energy is limited. And also the nature of the power sources is also stochastic or random, because you don't know how much energy the node may collect at a given time, because even though it might be daytime, it might be a cloudy day, it might be a rainy day, and so on. So the energy distribution is also uneven, because each node may have their own harvesting rate, or might be in a place where they receive less or more energy. So the research objective of energy harvesting wireless sensor network is to ensure that the network goes on for an infinitely long amount of time. Okay, so how to do that? We have to use the harvested energy appropriately so that it is feasible to meet the goal, and the goal is a long time network operation. And to ensure the network operation for a long time, a maximization of network remaining energy is important. So this means after the any operation is done, it must be ensured that the maximum amount of energy is left in the nodes. So we have to select that route or the specific action which ensures that after the action is done, the overall network energy level is the highest. Okay, and another thing is maximization of minimum energy levels in the network. Okay, so the first one was total network energy, and this one is the minimum energy level. So that means, let's say if I pass a packet through a specific route, maybe the overall energy used is very less, but a specific node in that route has a very less amount of battery life left. So it might be a better option to actually use another route where all the nodes have a significant amount of energy left. Okay, so these are two things which we have to consider, and these are the two promising factors which researchers usually look into. So energy harvesting wireless sensor networks has many applications, and as you can now restore your energy, you can also process or you can transmit a higher volume of data compared to before. And in these networks as well, the data is periodically forwarded to sync, and examples can be precision agriculture, wildlife monitoring. We have already seen these examples, and the requirement is, as we have already said, for perpetual network operation, the requirement is you have to maximize the total network remaining energy and the minimum energy levels as well. Okay, so what is a routing metric? A routing metric is a unit calculated by a routing protocol for selecting or rejecting, that means for selecting or not selecting a routing path for transferring data traffic. And examples we have already seen in the previous lecture, hop count, expected transmission count, right? So for satisfaction of certain energy objective of energy harvesting wireless sensor network, the routing metric should be aimed at these two things, that the things we have already discussed before, right? So in this scenario, the routing metric is based on energy levels instead of the delay. So there are already various existing route selection schemes in energy harvesting wireless sensor networks, and they consider a lot of things. They might consider the battery residual energy. So this means the amount of energy left in the node after a transmission is done. Then they also optimize the predicted harvest energy. That means they try to predict the amount of energy that a node harvests in a given time, and following or considering that it performs the let's say transmissions or selects the routes. And it might also consider the estimated energy consumption. So that means it estimates the amount of energy that is used when a transmission is done, and not the amount of energy left. Okay, so you might confuse the first and third point, but they're actually quite different. And then also the channel condition might be considered. So all these things, they are already done before this paper was proposed, and they are all very significant objectives. But when this paper was written, there was no significant research done on overcharge of battery, and overcharge of battery is not very unusual. So this paper specifically targets overcharge of battery, or we can also call it wastage of battery. So to understand wastage of battery, we have to see a few examples. So we can say that although the amount of energy we get from sun can be considered, or for any ambient environment may be considered infinite, but the battery capacity of the node is finite. Okay, so whenever an excess amount of charge is added to a finite capacity battery, then we get a wastage of energy. So let's see. For example, this is a battery, and we can say, or we can assume, that the green part of this battery is the energy level of the battery, and the white part is the unfilled, or the part which does not have any battery left. So if the total capacity of the battery is 1, and if the current energy level is 0.9, then we can say that 0.1 is the amount of battery energy which has been used already. So delta T here is the prediction horizon. So this means the amount of energy it can gain after a specific amount of time. So in this scenario, we can say that the harvested energy is 0.2. So once you add 0.2 and 0.9, what do you get? You actually get 1.1, but the total capacity of the battery is 1. So this means that the extra part, 0.1 battery life, is wasted. Okay, so this is the concept of battery wastage. Now considering the wastage of battery life is can be taken as an research objective as well, and it can provide us with an optimal solution as well, according to this paper. And this can be done by maximizing the utilization of harvested energy. So this means that we have to send data packets in such a way so that this wastage is minimized, and not just the overall battery usage, or let's say the residual battery left. Not only that, but this paper also considers the wastage, and it tries to minimize the wastage. So let's see how the previous case can be avoided if the battery is used. So we again go back to the previous scenario where the battery size is 1 and the present energy is 0.9, and we predict that it will harvest delta amount of energy. So the harvested energy is 0.2, and obviously the wastage was supposed to be 0.1, but now if we actually consume due to transmission that part, that means 0.1 battery life, then there is no wastage. Okay, so that means if we use this node for transmission instead of any other node, then its wastage can be minimized. Okay, so this is what this paper aims to do. So how does this actually change the route? Okay, so to understand the effect of this protocol on routing, we have to see another example which will be shown later on. So to understand that example, we have to go through these things. The first one is there are two components of wastage aware routing protocols. Okay, so the metric can be considered according to energy consumption due to packet transmission. Okay, so this means the amount of energy that is used when a packet is transmitted. Okay, and the second thing is the total network energy wastage due to battery overcharge. So this paper considers these two things. One is the usual energy consumption, and the second thing is also the energy wastage due to battery overcharge. So how does it solve, or how does it consider these two things? It chooses a route from a set of routes which ensures a minimum of total network energy wastage plus the path energy consumption due to transmission. So it adds the two factors that we just mentioned. It adds them up and tries to minimize their sum. Okay, so the total network energy wastage due to selection of, let's say, route omega I is the on path wastage of omega I plus the off path wastage of omega I. So omega I is the route through which the packet is transmitted, and on path wastage means the wastage along the path through which the packet has passed, and off path wastage means the wastage in all the other paths which are not part of this route. Okay, so we're going to see the example, so no need to get confused. So let's say in this scenario the source is S and the destination is D. So the route is in this case 1 and 2. So the data packet passes from S through 1 and 2 and then reaches D or destination. So the wastage on path for route for this specific route can be considered as the wastage which happens in node 1 and node 2 after utilizing those nodes. Okay, so that means when the data packet is passed through these nodes, the wastage that is done in node 1 and 2 is considered as wastage on path. And if we have another route which is not used, okay, so in this scenario the other route is 3, 4, 5, but that is not being used. The transmission is going through node 1 and 2. So if there is any wastage on those nodes, for example in 3, 4 and 5, then that is called the wastage off path. Okay, so you should understand this by now, right? So if the route was going through 3, 4, 5, then the wastage on path would be the wastage of node 3, 4 and 5, and the wastage off path would be for node 1 and 2. Is it clear? So what I'm saying is just the opposite of this scenario. Okay, so the total network energy wastage due to the selection of the route omega 1, which is the route 1, 2, is the on path wastage added with the off path wastage. Okay, so this is the routing metric that this paper uses. Okay, so let's calculate the cost for this example. So the route cost for path sigma is path transmission cost plus on path wastage in all the used node and off path wastage on all the unused node. Okay, so path transmission cost means the amount of energy used for transmission. On path wastage in all used node means the amount of energy wasted in all the nodes in the path, and off path wastage on all unused node means the wastage in all the nodes which are not in the path. Okay, so in the first node the battery level is 0.8, and after harvesting the battery level has increased by 0.1. So the wastage if this node is not used is 0. Okay, and if it is used for transmission, then each transmission uses up 0.1 battery life for this node. So if it is used for transmission, then it will lose 0.1 battery life, which means even after transmission and even before transmission, there is no wastage. Okay, so EW on 1 means if this node is used, then the wastage is 0, and EW off 1 means if this node is not used, then the wastage is 0. So the battery life for node 2 is 0.9, and similarly the energy harvested here is 0.1. okay, so we can understand from this as well that even if this node is used or not used, in both cases the wastage should be 0, because it also uses 0.1 battery life to send a transmission. Okay, so for both node 1 and 2, even if both the nodes are used or not used, the wastage is 0. okay, so if we calculate the route cost here, the route cost for path transmission is 0.1 and 0.1. They should be added, right? Because let me just mark it here, because this is the path link transmission cost for this link, and this is the transmission cost for this link. So if we sum them up, then this is what we get. This is the path transmission cost. Okay, then let's go through the other nodes. So for node 3, the energy level is 0.9 and the harvest rate is 0.2. So now we can understand, right? Previously it had only 0.1 battery life left which can be filled, but after harvesting it is harvesting 0.2 battery life. So that means 0.1 will be wasted if this node is not being used, and if it is being used, then that wasted energy will be used, so then there will be no wastage, right? You can see here. So the off path wastage is 0.1. that means if this node is not used, then the wastage for this node is 0.1, and if this node is used, the transmission cost is 0.1. so if this is used, then there will be no wastage. So then for node 4, the battery life is 0.85 and the harvest rate is 0.2. So similarly, if this node is not used, that means the off path wastage is 0.05, and if it is used, then it uses up 0.1 battery life for a transmission. So after using 0.1 battery life, there is no more wastage, right? So the on path wastage is 0. And for this node, the battery life is 0.6, so it harvests about 0.2 battery life, and if it is not used, then there is no wastage, because after harvesting the energy level reaches 0.8, and the transmission cost for this node is 0.1. so even after transmission there is no energy wastage. Okay, so now if we calculate for all these nodes, then we get two calculations. For the first one, that means if when the packet is going through this path, then if you can calculate, then the path transmission cost for this path is 0.1 here, 0.1 here. Okay, so we get 0.1 and 0.1, and the on path wastage, that means the wastage for node 1 and 2 is 0, right? We can see the on path here is 0 and the on path here is also 0, and the off path wastage here is 0.15. Why? Because there is some wastage here, 0.1 for off path and 0.05 here for off path. So if you add them up, then the wastage is 0.15, and if you add all of these up, then the route cost is 0.35. Now let's calculate, if we send the data through this path, then what do we get? So this path is 345 or sigma 345. So the path transmission cost is 1 here, 1 here, and 1 here. So that means 0.3, and the on path wastage is 0, because this uses up the energy, wasted energy here, and the wastage energy here as well. So the on path wastage is 0, 0, and 0. So there is no on path wastage here, but the off path wastage is also 0 here, because even if you do not use the nodes 1 and 2 here, even then there is no wastage here. So as a result, we can see that the overall route cost for this route is 0.3. So we can understand from this example that even though the path transmission cost for this path is only 0.2 and this one is 0.3. That means according to the path transmission cost, this is the best path. But if you consider both wastage and transmission cost, then this is the better path because this gives us the value 0.3. okay, so please go through this example again, and if you have any questions you can ask me. Okay, so we can clearly say that the path sigma 345, that means this path leads or gives us the minimum cost and maximum remaining energy. Okay, so this should be our best path and not 1 2. So that was the end of this lecture. So if you have any questions, feel free to ask in all the platforms. You already know about the platforms, right? So that's it. Assalamu alaikum everyone.